Section 1-2, Explorations with Patterns. In this section, we're going to talk about how to find patterns and how to determine if a pattern holds. We'll talk about both deductive and inductive reasoning. We'll talk about different types of sequences, specifically arithmetic, geometric, Fibonacci. We're going to talk about how to find the nth terms of some of these sequences, and also how to use differences to find a pattern when it's not an arithmetic or a geometric sequence. Inductive reasoning is when we make generalizations based on what we observe. I've got two equations on the screen here. 0 squared equals 0, and 1 squared equals 1. And from these two equations, I might decide to make a silly observation that any number squared is equal to itself. 0 squared, still 0. 1 squared, still 1. However, we're all pretty aware that that's not true. And to prove that conjecture wrong, we just need to find a counterexample. 2, for example. If I square 2, that's equal to 4. It's no longer equal to itself. This is a counterexample that ruins the conjecture. For inductive reasoning, the risk is always out there that a counterexample might exist. And it's not possible to check every single case, so it's a little bit risky with inductive reasoning for that reason. You might test hundreds and hundreds of cases and see that your conjecture is true, but there might be one case out there that's hiding from you that is the counterexample. So we need to be careful not to make conjectures with too few cases. Deductive reasoning, on the other hand, uses definitions, axioms, theorems, and logic to come to conclusions. So here I have 3 equations on the screen. Each equation is a sum of 3 consecutive numbers. And we'd like to try and make a conjecture about a pattern that will allow us to calculate the sum of 3 consecutive numbers without actually performing the addition. So 14 plus 15 plus 16, of course we could type that into a calculator. We could probably add it up in our heads, but can we find that sum without doing that? Same with 19 plus 20 plus 21. Same with 99 plus 100 plus 101, or any 3 consecutive numbers. Maybe we recognize that there is a pattern here, and it comes from the center number being multiplied by 3. 15 times 3 is 45. 20 times 3 is 60. 100 times 3 is 300. And you might be thinking to yourself, that feels a lot like inductive reasoning. And you're right. At this point, this has been inductive. But let's use deductive reasoning to find out if that inductive, intuitive thing that we just found is right all the time, or if these are 3 special cases. With deductive reasoning, we want to start with something very general. So the idea that we're adding 3 consecutive numbers, rather than picking 3 consecutive numbers, let's use a general form of that. So I have n as my first of the 3 consecutive numbers. If I add 1 to that, I'll get the second of the 3 consecutive numbers. If I added 2 to my first number, I'd get the third. So just to compare this to the examples at the top of the screen, if n was 14, 14 plus 1 would be our second term, and 14 plus 2 would be our third term. So 14, 15, 16. So this represents any 3 consecutive numbers. Now here's where the deductive reasoning comes in. I'm going to take that expression and simplify it using logic of mathematics. I see that I have 3 n terms, So I'm going to call that 3 times n. And then I have a 1 and a 2 that I can add together. I'll write that as plus 3. Now mathematically, I know these two expressions are exactly equal to each other. They look different, but they represent the same quantity. I also know that in mathematics I can factor out a greatest common factor. I have 3 times n in my first term. I'm going to write my second term as 3 times 1, so that I can see that there's a 3 in both of these terms. Factor that 3 out, I get n plus 1. N plus 1 just so happens to be the middle term. So really we're saying 3 times the middle number. And this doesn't matter which 3 consecutive numbers we pick, it will always be 3 times the middle number to get the sum of 3 consecutive numbers. That's pretty neat. Of the sequences that we're going to talk about in this section, arithmetic is the first one. A sequence is an ordered arrangement of numbers. An arithmetic sequence is an ordered arrangement of numbers where each term comes from adding a number to the previous term. This is a recursive pattern of adding the same number. So I've got 3 patterns on the screen, and I want to show you that they each follow this rule. My first sequence, 0 plus 1 to get my second term, 1 plus 1 to get my third term, add 1 again to get my fourth term, add 1 again to get my fifth term. These 3 dots are telling me that this pattern could go on forever. Before we look at the other 2 sequences, let's talk about some sequence notation. For some reason, we use the letter A to represent any term in the sequence, and then we use a small number hanging off at the bottom to tell us where in the pattern that term appears. So for example, A sub 3 represents the third term in the sequence. In this first sequence we're looking at, the third term, 1, 2, 3, the third term is 2. So A sub 3 is 2 for this sequence. A sub 5 would be 4. A sub 1 would be 0. For the second sequence on the screen, we know that it is not a plus 1 arithmetic sequence because 3 plus 1 does not bring us to 6. So we have to think about what the number is that we need to add to keep moving along this sequence. If you can see it, great. If you can't, don't worry, I'll show you a way to find it. And for this third sequence, it's also pretty tricky because I don't see the numbers growing. And if this is an add number sequence, I would expect my numbers to grow. Every arithmetic sequence has what we call a common difference. A common difference is where you have one term and you subtract the term that came before it. So in our first sequence, let's take a look at the common difference. I'll call it D. And let's use our fifth term minus our fourth term. That looks like 4 minus 3, which is 1. And we should check 2 pairs of terms. So let's check the common difference again, this time using A3 minus A2. A3 is 2. A2 is 1, so I have 2 minus 1, which also gives me that same number, 1. That's the number that we kept adding over and over to move on down the sequence. Let's use this idea to see if we can find the common difference for the other 2 sequences. Let's pick any 2 terms, A4 and A3. To find the common difference, I'll do A4 minus the term before it, which is A3. That looks like 12 minus 9. 12 minus 9 is 3. So we suspect this could be the common difference, but we should double check. Let's pick two more terms. How about A5 minus A4? That would be 15 minus 12. This is also 3. And if we really wanted to be sure, we could double check that adding 3 will take us all the way down the sequence, which it does. Let's look at the last sequence. 13, 11, 9, 7. To calculate a common difference here, let's pick any two terms, like A3 minus A2. That would be 9 minus 11. Now, it's really important to keep the order correct. A3 is further on down the sequence, so I need the 9 to be first, and then subtract the term before it. So 9 minus 11, that leaves us with -2. And that explains why our sequence wasn't growing, it was shrinking. Let's double check that we have that right. Let's pick A2 minus A1. That would be 11 minus 13. That's also -2. So this is an add sequence, but we're adding a -2. So adding a negative number looks like subtraction. And you could call it a subtract 2 sequence if you'd like, or add -2. The last thing we need to talk about with arithmetic sequences is the idea of a general term. Now, remember that we use a with a subscript to tell us where in the sequence we are. So if we want the nth term, then a sub n is representing the nth term. N is acting as a placeholder so that we can find any term we want. If we can find this general term, the nth term, then we can generate any sequence term that we want, even if we don't have the previous term. So for example, in the sequence, the middle sequence here, we said that the common difference, I'm going to write that as D, was equal to 3. I have the first 5 terms written on the screen. But what if I wanted to calculate the 11th term? That would be a sub 11. I can use the nth term, this general version, to find that, even if I don't calculate the next 5 terms in the sequence. All I need to do is follow the pattern. Now I'm going to show you where this pattern comes from, and then we're going to use it. So the pattern says to add the first term plus the common difference D times n minus 1. But let's see where that comes from. If we're continuing working on this second sequence on the screen, 3, 6, 9, 12, 15, etc., we know our first term, A1, is equal to 3. And we found in our pattern that the next term, A2, was just 3 plus 3. And that came from our first term, A1, plus 3. And then to find our third term, we took A2, which was A1 plus 3, so A2 plus 3, which is A1 plus 3, and then we're adding another 3 to it. So I've replaced A2 with A1 plus 3 because we found A2 using A1 plus 3. And we can rewrite this. If we have A1 plus 3 plus another 3, we could write that as A1 plus 2 times 3. And we can continue this pattern. A4 is going to come from A3 plus another 3. But we know that A3 is just A1 plus 2 times 3. And so we're adding 3 to that. Well, instead of writing 2 times 3 plus 3, why don't we write A1 plus 3 times 3? And then A5 would become A4 plus 3, but A4 is A1 plus 3 times 3, and we're adding 3 to that. So that's the same thing as A1 plus 3. I'm going to write the 4 in front. 4 times 3. And now I want to show you the pattern that's arising. After we've picked what A1 is, we've added 3 to it multiple times. And the number of times we're adding 3 is related to the position in the sequence. So for A2, I'm adding 3 once. For A3, I'm adding 3 twice. For A4, I'm adding 3 times. For A5, I'm adding 3 4 times. It seems that the pattern is, for every position in our term, we're adding 3 one less than that. So we could come up with a general form that says, start with our first term, then add our common difference times the term number n minus 1. Now that we see how to come up with this general form, we can use it to calculate, say, the 11th term. Our common difference was 3, so our general term looks like our first term, 3, plus our common difference, 3, times n minus 1. And then I can use my general term to find the 11th term just by replacing n with 11. So the 11th term looks like 3 plus 3 times 11 minus 1, which is 3 plus 3 times 10, which comes out to be 33. Any arithmetic sequence can fit into this general term. All we need to know are 2 things. We need to know what a sub 1 is. What is the first term in the sequence? That is super important. We have to know that or we can't calculate the general term. We also need to know the common difference. This is very crucial to finding the pattern, so we have to have that common difference or, again, we can't calculate the general term. Once we have those 2 things, the first term and the common difference, we plug them into this general term formula, and then we can use it, just like we did over here, to calculate whatever term in the sequence we wish. Arithmetic sequences are one example of a recursive sequence. But a recursive sequence is even more vague, because it's an arrangement of ordered numbers, where each term comes from some operation on one or more of the previous terms. Here's an example called the Fibonacci sequence. Looking at all of the terms, and there's quite a few here to look at, we can tell this is definitely not arithmetic because I can't add the same number to any consecutive terms to get the next term. So instead, I think maybe it could be a Fibonacci sequence. This one in particular says that you need to add the previous 2 terms to get the next term. So let's take a look at how this works. I'm going to call this first term f sub 1. F for Fibonacci, 1 because it's the first term in the sequence. I'm going to call this next term f sub 2. F again because it's Fibonacci, 2 because we are the second term in the sequence. My next term, I'll call that F3. The pattern that I'm seeing for this Fibonacci sequence is F1 plus F2 equals F3. And we can try to see if that pattern holds for any other 3 ordered terms. So let's identify this term as F4. And let's see if F2 plus F3 equals F4. Well, we have 1 plus 2. That definitely equals 3. So what we're seeing is that if you add 2 terms together that are next to each other, you'll get the term after them. The way that we would write the general form for this, f sub n being the general term of the sequence, says take a term, any term before n, and than the term before that. So the two examples we have here involving the first few terms of the sequence, I can check to make sure that my pattern holds. So let's try with this first one. F3 came from F1 plus F2. So let's see if we can replace n with 3 and see that we get the same result. So if n equals 3, then we have F3 equals F sub 3 minus 1 plus F sub 3 minus 2. 3 minus 1 is 2, so we really have F2 plus 3 minus 2 is 1, so that looks like F1. So that's the same equation that we made up when we were looking at the pattern for the first time. So a recursive sequence can be arithmetic, but it's not always arithmetic. Arithmetic sequences are always recursive, but recursive sequence does not have to be arithmetic. Fibonacci is an example of a recursive sequence that is not arithmetic. Geometric sequence is the next sequence that we'll talk about in this section. It again is an ordered arrangement of numbers. This time each term comes from multiplying a number to the previous term. So this again is a recursive pattern, but this time instead of adding the same number over and over, we're multiplying. Looking at our first sequence on the screen, we have 1, 2, 4, 8, 16. If we look for a multiplier that takes us from one term to the next, I can do 1 times 2 to get 2, 2 times 2 to get 4, 4 times 2 to get 8, 8 times 2 to get 16, etc. So that first sequence, we could call that a multiply by 2 pattern, or a geometric pattern with a common ratio of 2. Arithmetic patterns have a common difference. Geometric has a common ratio. Looking at our next pattern, this one's a little trickier. I'm saying multiply, but remember that we can multiply by fractions. 15 times 1/3 would be 5. 5 times 1/3 would be 5/3. 5/3 times 1/3 would be 5/9. 5/9 times 1/3 would be 5/27, and so on. This pattern, we might be tempted to call it divide by 3, but I want to encourage you to call this a multiply by 1/3. They really are the same thing, but because we're calling a geometric sequence a multiply pattern, it's a good idea to be consistent and call this a multiply by 1/3. Looking at our last sequence, we can see there's a typo. We should be alternating signs because the common ratio that I picked to make this sequence was a -3. So 2 times -3 is -6. -6 times -3 is +18. 18 times -3 would be -54, and so on. So this one has a multiply by -3. A common ratio is one term divided by the term before it. So if we're looking for a ratio, let's call it R, I'm going to take some term, a sub n, and divide it by a sub n minus 1. This could be something like a sub 7 divided by a sub 6, or a sub 11 divided by a sub 10. As long as the term on top is the one that's further along down the sequence, then we're going to be fine. And as long as the term on bottom is exactly the one before the term on top, we'll calculate our common ratio. So for any one of these sequences, we can calculate the common ratio. Let's go ahead and try a few. I'll pick term 4 and term 3 from our first sequence. The common ratio would look like 8 divided by 4, which is 2, exactly what we found. In the next sequence, I can pick any two terms. Oh boy, we're going to have to divide some fractions. Again, I'll pick the fourth and the third terms. This common ratio would look like 5/9 divided by 5/3. And if that feels overwhelming for you, grab a calculator, type it in. Otherwise, maybe you remember the rule. If two fractions must divide, flip the second one and multiply. Got to keep the fractions written correctly, though. That should be 3/5. The 5's divide off. I get 3/9. 3/9 is the same thing as 1/3. So we found the same common ratio. One last sequence to calculate the common ratio for. How about we use the third and the second terms for this one? So we'll have 18 divided by -6, and that comes out to be -3. So if we suspect that we have a geometric sequence, we should calculate the common ratio at least twice. For any one sequence, we should check that between two pairs of terms, the common ratio is the same. Now we can talk about the general form of a geometric sequence. Similar to an arithmetic sequence, we need two things, two bits of information to be able to write the nth term or the general term. Again, we need to know the first term, the starting point, and we also need to know the common ratio. Once we plug those two things in, we can calculate any term we want. So for our first sequence, our first term is 1. So 1 times our common ratio, which is 2, raised to the n minus 1 power. And we can double check that this is true for any one of the terms in our sequence. Let's try the fourth term. So we have a sub n equals 1 times 2 raised to the 4 minus 1 power. We'll simplify our exponent first. 1 times 2 cubed. Right here, sorry. 2 cubed is equal to 8. 1 times 8 is equal to 8. So our fourth term came out to be 8 using this general term, just like it shows in our sequence. The last type of pattern that we're going to talk about in this section comes from a difference technique. So I'm calling these difference sequences. Our book refers to some of these patterns using figurative numbers, but the fact that we're using differences, multiple ordered differences to find the pattern, that's what makes these so special. So the two sequences we have on the screen, they are not arithmetic, they are not geometric, they are not Fibonacci. So we have to come up with something else to see if we find a pattern. The difference technique says to calculate the common difference between any two consecutive terms. So we'll do 3 minus 1 to find 2, 6 minus 3 to find 3, 10 minus 6 to find 4, and 15 minus 10 to find 5. Now you might see a pattern already, which is awesome, but if you don't see a pattern, keep going. Find a second order difference. 3 minus 2 is 1. 4 minus 3 is 1. 5 minus 4 is 1. So we're seeing that there's a common difference of 1, and that's the second order difference. So this pattern comes from a second order difference that's equal to 1. On the right side of the screen, we have a different pattern. We'll try the differences technique again here and see how it goes. So 3 minus 2 is 1. 9 minus 3 is 6. 23 minus 9 is 14. 48 minus 23, 25. And then 87 minus 48 is 39. I do not see a pattern here at all. So we're going to go ahead and find another ordered difference. Let's change colors here so we can see a little more clearly. 6 minus 1 is 5. 14 minus 6 is 8. 25 minus 14 is 11. 39 minus 25 is 14. Not quite sure I see a pattern yet, so I'm going to go ahead and continue on with these ordered differences. 8 minus 5 is 3. 11 minus 8 is 3. Here it is. 14 minus 11 is 3. This is a third order difference, and the pattern is 3. So sometimes you're looking at a sequence and you see that it's clearly not arithmetic because they don't have a common difference right away. It's not Fibonacci. You can't find a pattern that uses previous terms. Or it's not geometric. There's no multiplier that takes you from one term to the next. We don't have a common ratio. Then we should try to do these ordered differences techniques to see if maybe it's the second order difference that has a pattern, or the third order difference that has a pattern.